Hey, welcome to the Swiftbird. I'm Yakov. Now that Apple has released all of this year's major OS updates, it's time to have a deeper look at what they can offer to us, developers. Recently, I published a video about the latest Swift update, version 5.9. One of the biggest features this time was macros, and in my video I give a brief overview of what they are about. I'll post a link to that video somewhere here, in case you need a refresher. It may come in handy, because today I'm going on a big journey to learn everything there is to know about Swift macros. I'll have a look at the vision behind them and some implementation details. And of course, I'll be writing a few macros of my own. Well, kinda. I initially filmed this as a single video, but the result turned out so loaded with details I decided to make it a two-parter instead. So in this video, I'll be having a look at macros in general, how they emerged, how they work, and how they fit into the big picture. And in part 2, which you'll see in a few days, I'll be writing, debugging, and testing my own macros. Again, this only came up in post, so the following narrative doesn't reflect this change of plan. If you're only interested in the tutorial part, you can skip to that section in the video. But I hope you'll join me on each step. Knowing how to use a tool is very helpful for practical tasks. But understanding why it was designed this way makes you a much better engineer. Besides, while I was doing the research and experimenting with my own macros, I found several caveats, which you'll understand better if you don't skip anything. If that sounds good, give this video a thumbs up, subscribe to the Swiftbird, and prepare for the ride. And if you want to see more of such content in the future, consider supporting this little channel at the links below. Ready? Now hold your breath, because we're taking a deep dive. My first stop on this journey is gonna be discovering the reason why macros were added in the first place. I mean, didn't Swift already offer us all the tools we need to create great software and in the meantime enjoy the process? There's actually a pull request in the Swift Evolution repo on GitHub. The document and this PR answers many questions about how macros came to be. I'll post a link in this video's description, so you can have a look later. But instead of just going through this document, I'd like to draw your attention to one global trend in the Swift evolution. If you look at its history from the very beginning, and especially if you compare Swift to Objective-C, you'll definitely see one idea that comes up over and over again. Take a look at this code. It's just one class method calling another one, right? Notice anything strange? Well, this code compiles and launches normally, but that doesn't mean it works the way I want it. It's quite the opposite, actually. The first method has a typo, so the second one will never be called. But Objective-C isn't really concerned. Because of its dynamic nature, it just assumes that some symbol will match the call at runtime. There's quite a few techniques for supplying implementations indirectly. Swizzling is one of them. This behavior doesn't make Objective-C a badly designed language, but its paradigms sometimes make it pretty hard to write, maintain, and debug code. So here's the same code in Swift. As soon as you try to call a method which doesn't exist, you get a compiler error. You'll notice something's wrong way before you even have a chance to run the app. Okay, you may say comparing Swift and Objective-C isn't fair. I kinda agree. They were created in very different eras of technological history. Then here's another example. That is how you decode JSON in Swift 3. And that is how you do it in Swift 4. The decodable protocol not only made the code more compact, but it also made it impossible to mess up property names. Once again, the responsibility for checking everything shifted from the runtime to the compiler. Key paths are another example, but I won't go into detail, you get the idea. Swift is becoming more static-oriented. In other words, more aspects are checked while you're writing the code, and fewer when the code is running. The benefits are clear. The feedback loops become shorter. You spend less time debugging and can more often write the correct code on the first try. Macros are another step in this direction. By using them, you can implement even more safety checks at build time. Besides, macros can reduce the amount of boilerplate, the code for common tests which you write over and over again. Hopefully, by the end of this video, you'll see how macros can make your work faster and more enjoyable. Now, let's talk about how macros work behind the scenes and what they can and cannot do with your code. At this point, it may be helpful to understand what happens with your code after you click the build button. I'm not going too deep into compiler design today, but I'll give you a simplified explanation tailored to this video's topic. By the way, let me know in the comments if you want an in-depth video about the Swift compiler. So, There are 3 steps we'll have a look at today. There's more in total, but the others aren't really important for macros. The first one is parsing. Even though Swift code is not an article or poem, it's still just plain text. It doesn't have a defined structure. While it stays like that, the compiler cannot do much with it. To fix this, the code is tokenized and transformed into an abstract syntax tree, or AST. The tokenizer goes through your code while paying attention to keywords, such as func, if, or return. These words declare operations which help construct the tree and define the relationships between its nodes. Here's what an AST may look like in the end. Once the tree is constructed, the compiler can understand and reason about it. If your code doesn't contain lexical errors, such as typos, missing returns, or unknown symbols, it can be compiled into machine code, a bunch of ones and zeros which the processor can execute. It's not really machine code at this point. Because the Swift compiler is based on LLVM, it uses the intermediate representation, sort of a universal language. The IR acts as a bridge between the language of your choice, be it Swift, Rust, C, or something else, and the processor architecture, ARM, x86, PowerPC, and many more. This is somewhat similar to the Java virtual machine, but in contrast, it allows the program to run at the native speed, without any runtime translation. I won't go any deeper, but I decided to highlight this mechanism because I believe it's such a cool feature. I'll leave a few links in the description, and I encourage you to have a look at them when you have time. Once the compiler's done its job, the linker comes into play. It looks for any outstanding references to external libraries and makes sure those calls are handled correctly. There's a few stages after that, but we're interested in the 3 steps I described. To be precise, in the gap between parsing and compilation. It's at this point that macros are enacted. And after compilation, it's as if they don't even exist, so remaining build phases occur just as always. Macros are basically separate programs. They are built independently of your app's code and run before the main compilation stage. Once the app code is transformed into an abstract syntax tree, but before it's turned into machine code, Swift macros get their chance to shine. They receive the part of the syntax tree belonging to the macro, and they transform it into a new structure. Besides the syntax tree, the macro implementation also receives any input you provided explicitly. Macros can add new code, which is then fed to the Swift compiler along with the original code. However, macros cannot modify or delete any existing code of your app. Moreover, they don't even have access to it. That's because macros run in a sandboxed environment, with no access to your source file, any other files on the disk, or the internet. Just like I said, macros are kept separate from everything else. This ensures predictable results, which is a huge plus. But it also means that the macro cannot see any code which comes before and after the call, so the macro's logic cannot take it into account. The macro code, as well as its input and output, are checked just like any Swift sources. If something's wrong, the macro build fails, which in turn triggers your entire build to fail. So by integrating macros, you assume additional responsibilities and risks. However, you can ask Swift to show the transformation process in detail. Thanks to that, macros are not some black box to you. I'll get back to macro debugging later in this video. Let's now have a closer look at how macros work. This process has 4 steps, and they are pretty straightforward. First, the compiler reads your app code and creates an in-memory representation of the syntax. It's the very same parsing step we discussed earlier. After that, the part of your code's AST relevant to the macro call is sent to the implementation. The implementation processes this AST and returns an updated structure. This process is called expansion. Next, the call returned from the macro is put back where the macro was called. The compiler basically replaces the macro call with its expanded form. And finally, the compiler takes the updated code and continues with the normal compilation. At this point, you can see how Swift compilation works in general, and how it integrates macros into the process. Before I start writing and calling macros, there's just a few more things I want to highlight. As you probably know, Swift offers 2 kinds of macros, attached and freestanding. They're similar in how they work at a high level, but they differ in where you can use them and what you can actually achieve by doing so. Attached macros modify the declaration they're used with, such as classes, properties, or methods. Without a declaration, attached macros don't make much sense and cannot be used. They can add new capabilities to the declaration. For example, they can define a new method or declare conformance to a protocol. Freestanding macros, in contrast, can be used all by themselves without being attached to some symbol. But there's more than one flavor of freestanding macros. There's actually 2. Declaration macros introduce new symbols, such as classes, and expression macros produce values or perform actions. An example of an action is compiler diagnostics, such as warnings or errors. Expression macros can trigger them based on some logic. The difference between declaration and expression macros is pretty significant, and it determines how you declare and implement the macros, which finally brings us to the part where I actually write, use, and debug some macros. And you'll see all of that in part 2 of this video. It should be out in a few days, but my main goal here is to make it as clear and detailed as possible, so I'm not rushing it, I'll be honest. In the meantime, let me know if you have any questions so I can answer them in the second part. Don't forget to subscribe and stay tuned for more.